Hello, welcome to Stat134, Lecture 23. Last time we finished section 4.2 on the gamma distribution. We talked about the exponential and gamma distribution. Some notes about the gamma distribution. We have the gamma function, which when r is a positive integer is just r minus 1 factorial. But the gamma distribution allows the parameter r to be any positive real number, and it can be shown using calculus that gamma of 1/2 is the square root of pi. So if r is a positive integer, t being gamma, is the time to the rth arrival. So the exponential lambda is equal to gamma r equals 1 lambda. And to find the probability that t is greater than t, a major idea is to realize that the event that t is greater than t is equivalent to the event that the number of arrivals in time t is less than r, and you can find the probability of that using the Poisson formula. So today we're going to cover section 4.4, skipping 4.3. First thing, we're going to talk about recognizing a distribution from the variable part of its density. And secondly, we'll discuss the change of variable formula for densities. Okay, so recognizing a distribution from the variable part of its density is an important skill. So a density can be written as a constant times a variable part. So the variable part is the part that it has t in it, where t is, right, f of t. And because the density integrates to 1, c is a function of h of t. So the constant can be found just from the variable part. So the density really is determined by its variable part. And often it's advantageous to ignore the constant part of a density and just work with the variable part, because the constant, it just clutters up the page and it doesn't allow your mind to focus on what's important. So here's a list of densities we've seen so far and their variable parts. So notice that the gamma distribution, the variable part is the form t to an exponent e to the minus lambda t, where t is greater than 0. T being normal has exponential, it has a t squared in it, and uniform has, for its variable part, an indicator where t, where the indicator is 1 exactly when t is in the interval a b. So now I had you guys practice recognizing what distribution a variable part of a density belongs to. So the first one being gamma r is 4, lambda is 1/2, because the exponent for t is r minus 1. And normal, and so e to the minus 1/2 t squared is just the standard normal. E to the minus 3t, recognize that as exponential, or gamma r is 1 lambda 3. T to the minus 1/2 e minus t is r to the 1/2. So whenever you see r to a negative power, that negative power needs to be less than 1, because for it to be gamma, it's r minus 1. So lastly, it's pretty clear that's the standard uniform. Okay, on to the change of variable formula for densities. This is a really important topic that comes up a lot. You make a transformation of a random variable and want to know what's the density for the transformed random variable. So allowing for the fact that y is g of x and that the function g is many to one, you will have a sum of terms, that your density will be a sum of terms. And I think it's best seen by this picture here, right from your book, in fact. So here's a function that's 3 to 1. So we have 3 x's that all map to the same y, and for y to be in dy, that's if and only if x is in dx1, or x is in dx2, or x is in dx3, and these are all mutually exclusive events, so the probabilities add just by the addition rule. And from this important formula that I'll highlight here, everything follows. So you can just then write this out in terms of the densities, and then divide both sides by dy. And so when dx dy is not 0, you can, its inverse is actually 1 over dx dy. So dx dy is 1 over dy dx, which you can also write as g prime of x. So that's what I've done here. And so this is the change of variable formula. Let me highlight this also. Okay, this is the change of variable formula, but notice that the right-hand side has x's in it. So you need to evaluate, so that's the part here, you need to now stick in x equals g inverse y in for the x's here to make them in terms of y. So let's see this in an example. Okay, so say that x is the standard normal. So I've written out the density here. And y is sigma x plus mu, where sigma is some change of scale. Sigma being positive. And we want to find the density of y. So here, notice that since sigma is positive, y equals sigma x plus mu is an increasing function. So it's monotonic. It's a 1-1 function. So our change of density formula is just going to have one term in it. And so now what we're going to do is now don't put in the entire density for f of x, just put in the variable part. So we'll stick in the constant at the end. So this will make things easier for you and less writing, less time. So I have the density of y at y is proportional to, that's what this alpha looking symbol means, proportional to. So on the numerator I have the variable part of the normal density divided by the derivative of sigma x plus mu, which is just sigma. Now evaluated at, so now I'm going to write x in terms of y. So x is y minus mu over sigma. So I'm going to substitute this now in for x. And that gives me 1 over sigma e to the minus 1/2 y minus mu over sigma quantity squared. And now to make this a density, I'm going to stick back the constant that I omitted in the beginning, which was 1 over the square root of 2 pi. I'm just put that back, and voila, you have the density of y. So notice you can find the expectation of y and the variance of y, and that's mu and sigma squared, respectively. We'll see later that y is normal, and hence y is actually the normal random variable with mean mu and variance sigma squared. Let's do another example. So let's let x be uniform on minus 2, 2. And so I've written out here the density for this. And of course, another way to write this density without the indicator is that it's 1 over 4 when x is between minus 2 and 2 and 0 otherwise. But it's helpful writing it this way because then I can just isolate the variable part. So notice I've just graphed here the function. So we want to find the density of y equals x squared. I've just made a quick graph of y equals x squared, and you can see that as x runs from minus 2 to 2, y runs from 0 to 4. So that'll be important. So f of y is proportional to, so I'm going to write in the numerator the variable part over the derivative of y equals x squared, which is 2x, evaluated at x equals the square root of y. Now that's the, right, this is our function y equals x squared is 2 to 1. So I'm going to have two terms in my change of variable formula. And the second term then is x is minus square root of y. I'm going to substitute in, and notice that I put in an absolute value here for the denominator because it's a density, it needs to be positive. So both of the terms are identical. So the right, so the 2 cancels here, and we just end up with this. And now I'm going to put back the constant, which is 1/4, and then I can write this in the usual way. So the formula for the density is 1 over 4 square root of y for y between 0 and 4. And I've just graphed that density for you here. So then we did a concept test. Let v be a standard normal random variable. The distribution of x equals v squared is gamma uniform or normal. So let's check. Okay, so I've written here the variable part of the standard normal, and so x is v squared, so v is plus or minus square root of x, and dx dv is 2v. So that's all you need. So the f of x is proportional to e to the minus v squared over 2 over the absolute value of 2v, where we're going to plug in plus or minus square root of x and sum, just like before. And just exactly like before, the 2's cancel, and the x to the minus 1/2 in the denominator, if you put it up in the numerator, it becomes x to the minus 1 over 2 then e to the minus 1/2 x, and you recognize that this is gamma. This is the variable part of gamma